In the last podcast, I was sitting facing the window and there was some light shining through my glasses, and the sticklers for quality of videos message me saying these things are not good. So I turned around and I'm looking at the wall, and hopefully the reflection is gone. Anyways, this is a nice new paper that focuses on the feedbacks in the Earth system, which can amplify the risks and thus also amplify the need for climate action. This is largely the group that focuses a lot on tipping points, and we have discussed that in another podcast before. This one focuses on the feedbacks, which we will go through here in a table. Many feedback loops significantly increase warming due to greenhouse gas emissions. However, not all of these feedbacks are fully accounted for in climate models. Thus, associated mitigation pathways could fail to sufficiently limit temperatures. A targeted expansion of research and an accelerated reduction of emissions are needed to minimize risks. So in the models, many feedbacks are automatically included or represented. You don't have to specifically add anything, like the temperature water vapor feedback, which is a fundamental principle, then the cloud feedback, rain feedback, dynamics and circulation feedback. All these things are in the system, but there are additional feedbacks. For example, if you add the carbon cycle, then the carbon cycle can be affected by the climate and the warming, changes in ocean heat uptake, land heat uptake, and so on, or carbon uptake, and then that can feed back to climate as well. So that feedback of carbon to climate can in fact be turned on or off. Similar for aerosols, direct feedbacks, indirect feedbacks, and so on. So some are fundamental feedbacks that are already represented, some are not explicitly represented, and those that are explicitly included because the system itself behaves in a way between temperature, humidity, clouds, rain, etc. They may not be done very well in the model, so you have to be aware of what is missing in terms of representation and what is not well represented. This paper is simply looking at the feedbacks that are there that can amplify some of the responses of global warming to the internal feedbacks. So the snow cover albedo feedback, for example, as the warming increases, you form ponds like this and you change snow cover extent, snow depth, etc., which has a quick change in albedo in this case, and can then absorb more energy and continue to amplify the warming. Similar to the sea ice albedo, permafrost thawing, for example, can release some of the greenhouse gases embedded in them, like methane and CO2, and they can also change the albedo, but there are also complications in terms of whether the permafrost thawing then leads to phytoplankton and more carbon sequestration due to photosynthesis. So this research is still going on. Insect outbreaks with the warming and delayed arrival of winter, the insect life cycles change and they begin to, for example, move to higher latitudes and last longer in the season. Then they can begin to devastate the vegetation and increase chances for wildfire, and feedbacks in terms of carbon uptake and increasing CO2 remaining in the atmosphere, etc. Peatland smolderings can go on for a long time, because it's basically hydrocarbon that's sitting there and can burn and produce all kinds of noxious and greenhouse gases. Wildfires can have a feedback. Cloud properties with global warming and changes in cloud optical properties and cloud heights, etc., also have a feedback. We don't know exactly whether that's a net negative feedback or a positive feedback in a global warming scenario, but great efforts are being done to see whether we can nail it down. Desertification can have positive feedbacks in terms of energy budgets and loss of carbon sequestration, and of course forest dieback as well. Okay, so I'm being a bit brief, but you can read the caption here. The map shows example locations where select positive feedback loops are likely operating. The full extent of the area and locations impacted by each feedback loop are not depicted. Feedback loop summaries: sea ice melting or not forming, decreasing albedo, okay, which I mentioned. Increasing thawing and decomposition feedback loops, increasing thawing and decomposition, increasing CO2 and methane emissions, and loss of sequestration. But as I said, these are more complicated than that, so we should be careful about simplifying too much. Drying and increasing vulnerability of fire and smoldering, decreasing soil organic carbon, increasing release of CO2 into the atmosphere, and decreasing carbon sequestration. Wildfire story is also complicated in the sense you have to look for duration of fires, frequency of fires, area covered, intensity, etc. And there is evidence that area covered may be increasing, numbers may not be increasing, but this is complicated by human efforts to manage forest fires or vegetation that's vulnerable to wildfires and so on and so forth. So that's what I read here. Increasing fire frequency and or severity, increasing CO2 emissions, loss of sequestration, and change in albedo. Changing cloud distribution and optical properties can alter cloud albedo and greenhouse effect. So as I said, we don't know exactly whether that's really a positive feedback, but this paper here claims it's a positive feedback, so we have to be careful. Increasing chronic acidification and hotter drought stress extremes leading to expanding deserts, decreasing CO2 sequestration, and increasing albedo. Again, something we have to look for. Increasing albedo, in fact, can reflect more sunlight. Deserts in general can have negative energy budget in terms of heating during the day and losing energy during the night because there are no clouds and outgoing long wave can go straight to space. Dieback of Amazon, boreal, and other forests, loss of sequestration, change in albedo, decreasing evapotranspiration. Changing insect distributions and abundances, decreased host tree defense can lead to loss of sequestration, change in albedo. And finally, decreasing snow cover can lead to decreasing albedo as well. We'll look at the table here on some of these things. So, summary list of feedback loops, 20 physical feedback loops. This is the feedback loops, effect of climate change and effect on climate change. So climate change triggers a response, and then that response in the Earth system then feeds back onto climate change, and they can be positive or negative, as you can see here. The Planck feedback, or the Stefan Boltzmann emission sigma T to the fourth, obviously with increasing temperature, heat loss rate through long wave radiation goes up, so that's a negative feedback. Water vapor, increasing water vapor content increases greenhouse effect, so that's a positive feedback. Sea ice albedo, we already talked about decreasing albedo and positive feedback, so more warming. Ice sheets, glacier ice sheet melting and instability, decreasing albedo and positive feedback. Sea level rise can decrease albedo via coastal submergence, so can be a positive feedback, but we have to see how significant this is. Snow cover, of course, reduces albedo and is a positive feedback. Delta cloud distribution and optical properties here is listed as a positive feedback, but you may want to do your own research because it is not really so obvious that the net cloud feedback is positive. Dust aerosol abundance is questionable because the albedo changes greenhouse effects and also other effects so this is dust and there are other aerosols as well. So we don't know very well whether that's a net positive or negative feedback. Ocean stratification increases, carbon uptake by the ocean can decrease, but phytoplankton response is more complicated because nitrogen fixers may respond better to reduce nutrient supply in the near surface and reduced phytoplankton photosynthesis of other kinds which require nutrients, whereas nitrogen fixers can directly work with dinitrogen. So here it's listed as positive feedback, but I would be more careful about it. Ocean circulation can weaken and surface temperature can increase, but we don't know whether it's a net positive or negative. Solubility pump, so atmospheric, which is the ocean's way of circulating carbon with temperature effects and circulation. So CO2 absorption by the ocean can go down, so that can be positive feedback, but this again is slightly uncertain and not so obvious in terms of if the Southern Ocean, for example, is already becoming a net is having a net reduction in carbon sink or not, and whether the tropical Pacific response being more La Nina like under global warming is taking up CO2 or increasing CO2 because of the outgassing from the ocean and so on and so forth. Methane hydrates, they can release methane into the atmosphere, can be a positive feedback, but this is something that's not triggered yet, so we have to watch out to see if there is a point at which they become a key player. Lapse rate, which is the temperature gradient in the atmosphere, so temperature altitude relationship, they can decrease with global mean temperature, change the stability of the atmosphere, and can be a negative feedback. Ice elevation, so ice sheet and glacier elevation can decrease, which means glacier and ice sheet melting can increase and albedo can decrease, so that can be a positive feedback. Antarctic rainfall can decrease, ice sheet extent and precipitation can increase, which affects not only albedo but deep ocean warming as well, so that can be a positive feedback. Sea ice growth, sea ice thickness reduction, and insulation reduction to the loss of ocean heat. So this can thin the ice growth rate and can become a negative feedback because albedo can decrease and ocean can absorb more heat, but that's a temporary sequestration anyways. Ozone can be lowered because of tropical lower stratospheric ozone, so unknown effects in terms of positive or negative feedbacks. Atmospheric reactions, atmospheric reaction rates change, greenhouse effects will change, but we don't know the net effect yet. Chemical weathering rates can increase and CO2 taken out of the atmosphere. This is a long-term geological timescale negative feedback in the system, which continues to be a negative feedback in the present time as well with global warming. And in fact, there are ideas of geoengineering saying we can grind up stones like olivines and spread them and accelerate the weathering rates and take out more CO2 as a engineering approach. There are some biological feedbacks, so peatlands, drying and fire, reducing soil carbon, so releasing more CO2 to the atmosphere can be a positive feedback. Wetlands, wetland areas can increase and precipitation can increase CO2 sequestration and methane emissions. So it's a kind of a toss-up there, depends on what happens. But actually a recent report argues that globally wetland areas have been lost, but anyway it's listed here as a positive feedback. You may want to follow up on that. Freshwater aquatic plant growth rates can increase methane emissions, be positive feedback. Forest diebacks of course are bad news, can reduce CO2 sequestration and albedo change will happen, so net effect can be positive, but one has to watch out. Northern greening, there is some evidence of increasing boreal forest area and Arctic vegetation, which can increase CO2 sequestration but reduce albedo. So that's positive feedback going in the same direction. So just remember that I should have made it clear. Positive feedback is where the initial perturbation is amplified. Negative feedback is where the initial perturbation is damped. So here positive feedback means northern greening can continue. Insects, insect ranges and abundances change, so CO2 sequestration can be reduced and albedo can be changed, but overall it can be a positive feedback to the insect population. Wildfire activity in some regions increasing, CO2 emissions increasing, albedo changes happening, overall positive feedback. And biologically volatile organic carbons, so they can decrease greenhouse effect and increase tropospheric ozone, so maybe a net negative feedback. And soil carbon or other loss of soil carbon can increase CO2 emissions and be a positive feedback. So this is effect on climate change, so just make sure we are in the right ballpark. So here again, permafrost can be positive, soil and plant evapotranspiration can affect latent heat loss, can be a positive feedback because it decreases latent heat loss and affects the energy exchange and moisture budget, energy budget. Microbes, CO2 and methane emissions are altered, increased, positive feedback. Plant stress, thermal stress and droughts, so plant mortality can increase, CO2 sequestration obviously will decrease, making it a positive feedback. Desertification, desert areas can increase, which means sequestration of CO2 is decreased, albedo changes, so net positive feedback is possible there. Sahara and Sahel greening, so rainfall in Sahara and Sahel can increase, CO2 sequestration by vegetation can increase, leading to a negative feedback. CO2 fertilization effect, where increased CO2 has an impact on net primary production, which can increase carbon uptake and be a negative feedback. Coastal productivity, ecosystem degradation is an issue, reducing coastal ecosystem carbon sequestration and becoming a positive feedback. So the other feedbacks here, metabolic rates, so phytoplankton respiration rates can increase. Similarly in the soil, heterotrophic respiration, increasing CO2 released into the atmosphere, so a positive feedback on climate change. Ocean biology can increase CO2 emissions, so reduce uptake. Sorry, let's make sure. Ocean CO2 can increase, acidification will increase, ocean warming, so we saw this before. Generally it's argued that net ocean uptake will decrease. So how will the net carbon ocean sink change? Ocean carbon sink, questionable. Phytoplankton, DMS, dimethyl sulfide, is a cloud condensation nuclei which can change cloud albedo, so but we don't know the net effect there either. So summarize, the first step in curbing the near-term climate impacts and minimizing the risk of an eventual catastrophic outcome is for us to expand our awareness of the severity of our predicament. Thus, we have described an extensive set of potentially harmful feedback loops to increase our understanding, justify a more serious response, and motivate work to less probable but dangerously underexplored scenarios. It's too late to fully prevent the pain of climate change, as severe impacts are already getting felt. But if we can have a much better understanding of feedback loops and make the needed transformations, but if we can have a much better understanding of feedback loops and make the needed transformative changes soon while prioritizing basic human needs, there might still be time to limit the harm. Even if it turns out that feedbacks are already sufficiently characterized, these changes will provide enormous benefits to human well-being and the entire biosphere. Nature restoration is a co-benefit. Conversely, if the worst-case risks proposed by feedback loops and tipping points have been underestimated, the future of a hospitable planet, Earth, may be at stake. So this is the same group that works on tipping points, as I said, and I have raised some issues about that elsewhere, but in this context the focus is on the feedback loops, and these are important feedback loops. Models represent a lot of them, maybe not exactly correctly, so we always have that uncertainty. But the thing to remember is that with global warming projections, the model uncertainties dominate in the first couple of decades, and then the scenario uncertainties become completely dominant after, let's say, 2050 or so. So the scenarios can be designed as we want, and they dominate the projections quite a bit. So that's something we have to worry about as well. Okay, let's leave it here.